Okay, so this is kind of a, it was designed to be an autonomous talk, so it does talk about the same technology that the previous talk described. So I have some slides that are going to be a little bit overlapping, so I'll try to gloss over them depending on who was here and who was not. Who did not attend the previous talk right before? Okay, so we should go into all of it. All right. So the agenda is first, I'm going to do an overview of that knowledge-oriented platform that we built at GRAKN AI, and then I'm going to talk about analytics in general, what types of business problems we solve with analytics queries, and then I'm going to give some examples, and most, I guess, interesting part, at least for me, of the talk is going to be diving into the implementation of some of those analytics algorithms. I don't find them trivial, I find them kind of unusually interesting. Pregel types algorithms, I think it will be interesting to go into some of them. So, as an overview, we at GRAKN AI, this is a new knowledge-oriented platform that we built. It's kind of a hybrid graph relational model, so sort of inspired by topic maps. There is a unifying construct where we say that everything is a concept, and then we have different types of concepts. We have n-ary relations between entities and resources, and we have this notion of a knowledge base on top of a graph database, which is made up of ontology, rules, and data. The ontology is made up of several hierarchies, of entity types, relation types, and the relata types, the types of the components that go into a relation. And we have rules, which are basically form clauses. So using that, we have a mathematical formalism that describes exactly how that works and why, when the inferences that we can make from it are logically correct, etc. And we built a few tools to allow people to operate with that formalism. So we have a scalable distributed knowledge graph. We have the query language that we developed, and we have reasoning inference. And the part that I'm going to talk more about in this talk is analytics algorithms. So here's an example of ontology. As I mentioned, we have several type hierarchies. So in yellow, we have a hierarchy of entities. So we have person, event, different types of events, and then we have another top-level thing that we have is in the green, that's a relation. We have a type of relation which expresses that a person participates, that the person has participated in an event. And then the other type of another type of hierarchy is the hierarchy of roles. So we describe the participants in the relation via roles. Roles are essentially labels, but they do have this typing relationships with each other. Here's an example of a rule. So this is a if-then rule that basically says if we have a bird event with a high confidence and we have before the name of the person is something, and we have a relationship between an event and a participant in that event, and that relationship describes a newborn, then the name of the person is the name on the birth certificate. And this is a quick example of data that we visualized with our visualization tool, basically showing a few events and implementation. So this is as much as I will go into describing the knowledge formalism, because all we need to know is that we have a graph database and we have the means to express a logical formalism on top of it, ontology and data groups. So what about analytics? What are the types of analytics that we can do? So in general, analytics is about summarizing data, extracting different types of information from it. And in the case of graphs, we have the typical graph, the data summarization, computing averages and sums and stuff like this over sets of numbers. But we also have structural patterns that are of interest in a graph. and those are kind of new and different, and you know, in the data management world. And to give like the ground a little bit, the need for that, I'm gonna just give you a few examples of business questions that can be answered with this type of analytics. So one very kind of buzzword, you know, domain these days is customer 360, which is this idea that you can collect information about customers from many different sources, you know, their online behaviors, their transactions, what they bought, their social networking connections, their profiles, and stuff like this. And then you can ask the question: so, what products do highly influential people like? Right? And then you can compute that by first defining what highly influential means, and you do that by using some graph centrality measure around it. A very simple one is just the degree of how many things happening. Another one is popular page rank, obviously. So once we've identified what are the influential people, then we can, you know, filter and find out the products that they've rated above a certain threshold. Another group, and another example, what are the groups of people who are men and have common interests, right? And here is, we have a graph of people, and they're connected by shared interest, and then we would compute connected components in the graph, or clusters in the graph. And then we can target, you know, people with the same interest, for example, some market target. Another domain, which is a gold mine for knowledge representation, is the Biomedical domain. Simply because of the sheer complexity of the knowledge model there. So, you know, I'm just throwing in, you know, terms here. Like we have feelings, symptoms, treatments, drug side effects, physiology, drug interactions. All sorts of, you know, subgraphs like metabolic pathways and regulatory gene networks and stuff like that. So an example here could be like we want to find out whether a given drug can activate a specific gene, right? And this is kind of a path type of query where we could use a gene regulatory network where we have, you know, transcription factors. Those are types of proteins that activate genes. So we know what protein activates what gene, and then when that gene gets activated, manufactures a new protein which activates another gene, etc. We combine this with a metabolic you know, pathway graph, then we can figure out what chemical triggers what response. So those are the types of queries that are analytical in nature, and that we can, you know, compute with graph analytics. So in Graql is the language that is used on top of that is used to manage the knowledge representation that I mentioned, that we described earlier. We have two different constructs in the language to do analytics. One is a very standard conventional one. The microphone is not slow. I can't hear. Oh, okay. Okay, so this is different. Were you guys hearing me well or not? It was mine? Yeah?
Is GRAKN, are you all able to infer relationships to do entity resolution? Is that a part of
what resolution? Right?
So on the customer 360 bit, right? You had data aggregation, and then you had like some, you know, use case around what products will highly influence people like. Yeah. Right? But are you inferring relationships that this person's the same as this person's the same as this person, like entity resolution, or are you?
No, we don't. No.
Oh, okay.
No. This is. I mean, we work with the data. I mean, we. The platform itself does not will not have something like this right now. We we can define rules and you can define things on top to implement.
Okay.
Match.
That helps. Thank you.
Okay, so we have the typical analytics type construct where you run a query, you find a bunch of results, and then you aggregate them. Somehow, this is what you have in SQL with the group by and then the other one is when we basically work on the whole graph at the same time, and we use a massively parallel algorithm to traverse the graph, and then we compute some sort of analytics result. So this we do with two types of algorithms: MapReduce algorithm or a Pregel-like BSP algorithm. And I'm not going to that one in detail. So this is an few examples. Like the first one is an example of an aggregate query. So here, this is basically a graph pattern being matched, where we look for checking accounts that are owned by people who live in Senegal, right? And then we compute the poorest and the smallest each account in the largest one of dollars. And so we can perform several aggregates at the same time because there's no other place. So this will run, basically will get all the results in one place and then compute the aggregate there. And a more performant version would be the compute queries, which again, depending on the algorithm selected, will have a different implementation. So we use MapReduce for some algorithms, for example, for the mean. I'll give you an example here to compute the mean in certain types in ontology. That we use MapReduce, and then the computing connected components we use a BSP version. So, what are the challenges in implementing these types of algorithms? In a distributed graph, in a truly distributed graph, you don't really know where the data resides. I mean, the graph is the data is partitioned on different machines. So here I'm depicting, two hypothetical machines that share some data, that share one vertex, for example. The other vertices are, are not shared between the two machines. And there is no optimal partition of the data between machines for all conceivable computations, right? So for all practical purposes, the way the data is distributed is pretty random. So we can't implement an algorithm that simply does a sequential traversal, because the cost of that is very unpredictable. We don't know, to be jumped from one machine to another constantly. So we can't really implement an analytics graph algorithm that will work on a single time. It's just too expensive. So hence the massively parallel algorithm. So the important takeaway for massive parallelization is that what we want to do is we want to move code. We want to move the program to the data rather than the other way around. So and this is what the frameworks of Pregel-like frameworks allow you to do. So this way we parallelize the computation with the data distribution, and then when we want to aggregate results, we first aggregate locally, and then once we've done that, we then send over to the network and aggregate globally. Now, another point to remember is when we are implementing an algorithm, we try to avoid having shared global state because it's very expensive to maintain. In general, that's impossible to avoid, completely, but we try to minimize. So the next part of the talk is. And I'm going to go into a fair amount of detail in implementations of a few algorithms that we have, so you get a sense of the difficulty that goes into that. And if you were here on the last talk, Heiko mentioned, you want to do this yourself, it's easy. We have it out of the box. So and that, and also I think it's interesting to kind of examine them and to talk about it and see how those things work. So we're using the Tinkerpop framework. How many people here are familiar with Tinkerpop? Okay, about half. So this is an API that abstracts over property graphs, and the idea is that you have this API and the different vendors that implement it, so you can switch the implementation of the database in the middle. But in addition to just doing the data model stuff, the Tinkerpop recently added something called the GraphComputer, which is essentially a framework to do distributed computing over graphs. So the way the GraphComputer works is it uses Hadoop and Spark, and it loads the whole graph in memory initially, and then you can say, I want to run this BSP algorithm, and I'll explain what BSP is for those who don't know. It's like the algorithm framework, and then you run a sequence of MapReduce operations after that. So the BSP algorithm is what's known as the VertexProgram. So the one thing I wanted to say here is that Hadoop and Spark are used in Tinkerpop, and that initial load time that I mentioned is kind of its performance quite a bit. And for those of you that that I kind of is a red flag, I know things on Tinkerpop's roadmap to remove that and to kind of have a bit more intelligent there. So first, just a quick recap of MapReduce. I'm sure that probably all of you know what that is and how it works. In the case of graphs, we basically have a collection of vertices that we operate on, and we typically use that framework for numeric computations. And it works by doing a single cycle of computation. We map initially the data according to different keys, and then we combine it locally, which is kind of a local reduce operation, and then we call a reduce where all the data for a given key is computed, some function is computed. So we, for a lot of those algorithms like min, max, sum, etc., it's very simple. They can be done actually simultaneously in parallel. And what we do, we just say we just have one key during the mapping. That's just the name of the function. We say we mean that's the key, and then we just get the data and use the framework just to give us all the data in one place, and then we can just compute the function already. So that's not very interesting. But it doesn't work well because we have all the infrastructure already to do it. The algorithms like this are very simple. The more interesting one that we're going to talk about now is the BSP, the Pregel algorithms. So again, the question: how many are familiar with Pregel, how it works, and what should we do? Not many. Okay, so good thing that I reserved half the talk just because I find it very interesting. I think as we're moving towards bigger and bigger data sets, and as we're adopting graph databases, I think more developers need to be familiar with this mindset of thinking of implementing massively parallel algorithms. I think it's interesting. So we'll talk about it. So BSP stands for Bulk Synchronous Parallel, and bulk means that we're processing vertices in bulk, and we also are communicating in bulk over the network. Synchronous means that we divide the computation in separate individual steps, and we synchronize in between steps so that we know that previous step is due before we proceed to the next one. There was another framework fairly popular for parallel computation called message passing interface, which is a bit lower level, but you might have heard of it. It's kind of a similar idea of having one program that operates with multiple data. We also have the actor model, which you probably have heard of, where you have autonomous agents, actors that do one thing for one program, and they send messages to each other, and the computation is driven by an algorithm that that's implemented on top of that and after sending messages. So here, this is a bit similar, except we have this idea of synchronization between computation steps. And that's very important. So the messages are exchanged. We do it in one shot, and we know that that's done. So this makes it more predictable and more manageable. So the way it works is that we say that every vertex in the graph runs a program on its own, and then when it runs that program, it can send messages to other vertices, and it can change its properties, or you can write to a global memory that the framework will show that everybody sees the same global memory. And so the stages look like this. We start with, on the left-hand side here, we start with the graph, and then we partition it into subsets. We look at that application into subsets. Each one is assigned to a worker, which is on a different machine, and the worker will run through the vertices and run that VertexProgram on each and every vertex to give it a chance to receive messages that have been sent to the previous step, send messages that are going to be received from the next step, and modify the global memory maybe. So when So that's just what it was. You know, everything, all the messages get completed and all the writing gets completed before we move on to the next step. So when everybody says, I'm done, I have nothing else to do, then the whole global computation stops. So this is a simplified Java interface that VertexProgram, so you can see what it involves when implemented. You have to, you know, perform some initialization in giving that global memory object where you can, you know, apply some initial data. That's the first thing that you have. Then you can, then you define basically the block of the computation that execute as the iteration step. And there, you're given the vertex, you're given the object that allows you to send two messages, and you give that global memory object as well. And the terminate method says it's called after each step, and it asks whether we're done or not. So that's all for whole workers. So you do something to check the global state, you basically decide if it's algorithm or not. And then there are a few options here that I've shown that you can configure the framework. So we're not too concerned about that. So a few things that I want to say about this global memory. So this kind of an object is like a key value map that you can read and write. But has a few interesting properties. One of them is that it gives you the current iteration, so you know exactly which state you are in the vertex. The other one is that you can write the other problem any value you want, and just basically whoever is kind of a bit random, if multiple writers write the same on the same key, it's just the last one that is going to be used, and that's a bit random which one is chosen. And then the more interesting part is that we can change state of those values in the map from multiple vertices, and by if we use conflict-free iterations. So if two nodes, for example, decide to add something to a counter, because it's a metonic, you know, it's community operation, then both of them will work in way. Same thing with logical and OR operators. We can do an AND or an OR with the current value, and because of the community, we can do it for multiple nodes. All right, so now I'm going to talk in detail about two of the algorithms. One is connected components. It's kind of it's actually relatively simple compared to the other one, and I'm not sure how much time I'll have to the other one, but let's go through this one. So connected components is in the graph structure you basically want to find out what are the clusters of nodes that are, so you can, for any node it's connected to you can have a path to any node. This is kind of a building block for lots of parallel algorithms in graph processing. And they mentioned here, for example, you want to have a coloring, you can do that. So the classical algorithm, the sequential algorithm of your clusters is based on that first step. There is something called the Argent algorithm, which is that first reversal, and then you examine the stack that was accumulated during that first reversal to extract the connected components. So this does not translate very easily into a massively parallel setting, right? Because we have these data structures, right? We traverse the graph and we accumulate the visited nodes, and then if you want to know what are the next ones to be visited, we have to maintain the sets of nodes that we have to visit. So this requires a lot of usage of that global shared memory object, and it can get very big, so it doesn't work that way. So how would we do it if you want to use that VertexProgram type of framework where every vertex implements some logic exchanging messages with other vertices? So here's how it works. Here's the idea. What we want to do is we want to construct sets of vertices that are reachable from other set members. And the way we construct that set is we're not going to use a data structure, we're not going to use a cache map or an array or something. We're just going to assign them labels. We want to make sure that at the end of the computation, we have vertices that are labeled by the cluster to which they belong, by the time to count to they belong. So we propagate those labels to each step, and the way the algorithm works is that we assume that the labels have a natural ordering, so we have an easy way to pick one when we're trying to combine two components together. That's what we do. If you find the two separate components are connected, we can connect between them, and they have different tables, we pick the max of the labels, and we end up doing it together. So that's the idea. We use the vertex ID themselves for the labels, and then whoever has the max vertex ID, just the natural string ordering, will be the label of the cluster. So the way on the right hand side here, basically you find the start step and the start, the step of each stage, and then the combination condition. So when you start, each vertex sets its own ID as the cluster level, so because each vertex belongs at least to a cluster containing itself. And then it sends its own ID to all of the neighbors. Then on the next, on the step, during each computation, what we do is we examine the incoming messages. Those other vertices, our neighbors, send us messages, and they send us their labels, right, or the labels of the cluster they belong to. So we read that, and then we pick the max label of that, and we see is that new label the same as the one we already had. If it's not, then we update our label, and we send it to our neighbors. So this way the labels get propagated, and because we always pick the max, we end up with a new label assigned to a cluster. So if the label hasn't changed, if we receive a message and there's no label, then we go to Hoare. We say we have nothing more to do. So the whole computation terminates when all vertices are voted to Hoare. The way that voting works is by doing a logical end operation to that global memory. That's what I mentioned, is that you have this ability to, instead of accumulating the votes in the global memory, and every vertex has to add another piece of data, it's just only the logical operation. So that's that. So the next one is more complicated. I'm gonna get into it, and I hope so far it makes sense. I mean, do you guys have any questions? Do you kind of understand how that works? And yeah. So here's the algorithm to implement the median. So the median is a typical analytics type statistic that one wants. Does anybody not know what the median is? Okay. So the classical sequential algorithm to compute the median, and one of actually I've shown it here because it is an inspiration for the Pregel variable. And what's interesting here is, again, how do we avoid keeping these large data structures with these sets and stacks and stuff that we do in the typical sequential algorithm. So here, this algorithm is called quicksort. It's invented by the same guy that developed quicksort. And it works in a very, very similar way. We start with a list of numbers that we want to compute the median of, and then we pick a random element of that list, and then we condition the list based on that random element. We put everything small, meaning on the left side, the beginning of the list, and then bigger on the right. And if it turns out that the element that we picked is exactly the index position in the list is exactly half of the list size, then we found the median. Otherwise, we recursively go to the bigger set left or right. So in the partitioning, works in an obvious way, right? We just compare, we just look through all elements and compare with the pivot and decide whether we put the junior or the other to this big or small. So this is a sequential algorithm. It has kind of a basic structure that you try to imitate in the Pregel-like version. So here's what our organization does in English. So the English figure out an element. Then we divide the set into two. We have the left set with all elements less than the given key. The right set with all elements greater than the given key. And then if the median falls in the rest subset, then we use that to the next step of the equation. If it falls in the right subset, then we do that. Otherwise, we found. And we decide whether it's in the left or right subset based on the index position of the field. So, here's what we do to develop the master parallel version. Again, managing sets of values is best done by using levels, for instance. And that's one of the interesting, parts of this type of algorithm, so that you think what is important when you have a set. Is it important to have all elements like in somewhere in one piece of memory next to each other? Or is it like just the abstract operations of the set important? Like you have something that represents the set, identifies, and you need to know whether something is a member of that set. Okay? And that's usually what you need to know. This is what those levels do. You have a level of the vertex, that level tells you that the vertex belongs to a set or not. So we use that, and then the way we proceed, we imagine that we have a whole list of values, even though we don't really construct this. We imagine that we have it, and we maintain the positions, beginning and positions of that list exactly as in the sequential version. So the first thing we do, we put the pivot again, and we compute the left and right sets globally for each iteration, and then we use the sizes of this left and right set to update the indices of the beginning positions and decide which way to go. And in the sequential version, we stop when the median is falls exactly between the indices, so we're not inadequate. So the algorithm is right here. I'm gonna probably just kind of give the gist of it. I started out on the slide, not because I want to go into detail. Just sort of a scenario go through. But basically what we do, if you look at the start type and the aspect side, the start step, those are the things that we need to prepare in global memory. Right? We need to know, we need some way of identifying the current set we're operating on. And that's just simply a label. That's nothing more than that. And because we have the iteration number on every step of the computation, we can use that iteration number to identify near iteration 10, and on the left hand side or the right hand side, we can use plus or minus 10 to say the right or left. So in this way we know exactly where we are. And this whole list of values that we have in the sequential version is kind of a little bit, it is imaginary. It's not really constructed. We just maintain the essential properties of it. We just use the essential properties of that global list in our computation. So the other part that we need is the sizes of the set of elements small into the field. So knowing those sizes allows us to adjust the position in the list where we are. So what happens during each step? We basically check if the vertex we're currently examining belongs to the set we are currently processing. So this is we check set membership by using those labels. Then the next thing we do, we examine whether the value of the vertex is less reflected in the field. So what happens if it's less in the field? That means we have to put our vertex on the left set, and it's smaller in the field. So here's how that's done. The way we do that is we say, okay, from here on the next level of the computation, this vertex will belong to the set variable that was the direction. So this way we say this vertex belongs to the set value smaller than field. That's it. And then we implement the number of elements in the left set. And this can be done again because of those globally used operations within the global memory. And then we set the field number, the field value for the next iteration. We're saying the field for the left set is going to be the one of these vertex. So doing this means writing to the global memory. And because whoever last writes, depending on network conditions, etc., we're effectively picking a random field for the left-hand side, for the left side. So this is the same logic as the sequential version, except it's written and it behaves kind of different. Then the synchronize step where we're done. We're done with the vertex program, the study vertex program, and we need to decide whether we are doing the computation or not. At that point, all vertices have completed their logic. So we have the total number of elements of the left and total number of elements of the right. And so we can adjust the indices here, and we can say, okay, now I'm shrinking my list, and I'm moving, I'm choosing to go left and choosing to go right. So I think I'm gonna stop here with that description. There is the we're gonna put the slides up, but I think it's kind of instructive, I find, to try to figure out how you go from something fairly easy to follow logically and try to come up with a parallelized version of it, and try to think in those abstract terms where things don't have to exist exactly in memory, so they can just be absolutely defined and operated on logically. What time is it? It's I had some planning to do a demo. I'm not sure if I should show some queries. Let's do that. I need to start. How many times we started at? Started at 5:10, and now it's. Do we have time already to do some? What's going on here? Where is it? Okay, so I'm finding the server here. So the demo is going to show, just a few examples of Graql queries and analytics. So here's an example of a query where we just find people by their first and last name. So we can do something that's like typically SQL-like. I just prepared the two queries here to look. So this is a compute query, computing the shortest path between two entities, and it's using just a certain subset of the relationship types. So as I mentioned, it's the issue with that initialization time is that there is this Hadoop and Spark process that gets started and that has to load the whole graph. So now I think, oops. I think my resolution is strong because of the presentation here. But this is computing the shortest path between two people by using marriages and in parent-child relation. So somebody's son or daughter or married, then they're connected to the computer. The dataset here is genealogy dataset where we have people with their ancestry and also some documents and events that happened in their life. So actually, what I should do? So this is let me show you just a few more. This is another match query where we're basically trying to find people that are married more than once. So we compute we find elements that are in the marriage relationship with two different other elements that are, we don't really care to constrain here. That's because the marriage relationship itself constrains it. So there is a centrality measure here. We want to compute the degrees of people, grandparents and parents and marriages, etc. We can get that. Another one. Okay, let's do a median computation as well. So this is a web-based interface of the Graql language, so we can get results in either in tabular format or in the graph. So that's that's it. Just wanted to show that it works. Okay. Okay. I think we should stop here. Thanks, guys.